All right, let's jump right into this explainer. We're going to be looking at a microscopic infiltrator that honestly pulls off one of the most brilliant, lifelong heists in human biology. We are talking about a pathogen that has spent over 100 million years perfectly fine-tuning its ability to break into our bodies, completely sidestep our most advanced immune defenses, and just set up a permanent residence inside us.
So, think about this for a second. What does a childhood itch have in common with agonizing adult nerve pain? It kind of sounds like a trick question, right? But the answer actually reveals the incredible dual identity of the varicella zoster virus, or VZV. Because to truly understand this virus, we can't just look at how it operates over a few days. We have to look at how it plays the long game over the course of an entire human lifetime.
You know, there's an old, slightly grim saying in medicine. Herpes is forever. And well, biologically speaking, that is absolutely spot on. See, most viruses we run into, like your standard common cold, they're just these tiny RNA critters. They infect us, our immune system clears them out, and boom, they're gone for good. But the herpes family is playing a totally different game. They literally become a part of us by parking their double-stranded DNA directly inside our cell's nuclei.
And the absolute key to understanding how VZV does this is the concept of latency. It comes from the Latin word latere, which literally means to lie hidden. Normally, a virus will just break a cell apart to release its clones. That violent process is called the lytic phase. But VZV has this wild second trick. It can literally hit the pause button, tuck its DNA into a little circular episome inside the nucleus, and just wait silently for decades.
So let's break this down. Phase 1 is the initial breach, which is medically known as varicella.
Most of us just call this initial invasion the chickenpox, but underneath that acute respiratory infection is a crazy, stealthy 14-day incubation period. And 14 days is an eternity for a virus. It enters through our respiratory tract, gets picked up and carried to the lymph tissue, eventually floods the bloodstream, and finally gets deposited out into the skin dermis. And it manages to do this entire cross-body road trip totally under the radar of our immune system.
But what's truly mind-blowing is how the virus actually cracks the vault of our cells, the nucleus. The virus carries these special tegament proteins that act exactly like a microscopic lockpicking kit. They hook the viral payload onto the cell's internal microtubule tracks, basically riding them like a train right past all the cytoplasmic alarms. Once it hits the nucleus, it literally unzips the nuclear pore, drops its DNA inside, and rounds up to begin the takeover.
And the counterintelligence here is just next level. Normally, if a cell realizes it's infected, it'll kill itself to stop the virus from spreading, a process we call apoptosis. Well, VZV actually manipulates that. It delays cell death just long enough to ensure it can replicate and then triggers the self-destruct later for a clean escape. It even boosts an enzyme called SOX3 to muffle the body's interferon alarms and chemically blinds the natural killer cells that are sent to destroy it.
Which leads us to my absolute favorite part. It's like something straight out of a Hollywood heist movie. We call it hijacking the police car, because the virus can actually blind those natural killer and dendritic cells. Instead of being destroyed by them, it literally climbs inside. It uses our own frontline immune defenders as getaway drivers, traveling completely unmolested around the body to set up shop wherever it wants.
Which brings us to phase 2, deep cover.
Once that itchy childhood rash fades, the virus has officially won the first battle, and it retreats to execute its master stroke. To survive forever, it needs a forever home. Standard host cells are no good because they constantly die, slough off, and get replaced. If the virus hid there, it'd be thrown out with the trash. So instead, it travels to sensory nerve cells, often the upper branch of the trigeminal nerve near your eye. These cells last your entire life. The virus settles in and simply goes to sleep.
And that quiet retreat sets the stage for phase 3, the second strike, otherwise known as zoster. Decades can pass in total silence, but then, driven by the natural aging process, intense emotional stress, or maybe an immunosuppressive illness, our immune system drops its guard. And the crazy statistic here is that for roughly 30% of adults over the age of 50, this dormant infiltrator is going to wake up. And when it does, it transforms into something much more malevolent, shingles. When it reactivates, it travels all the way back down that exact same sensory nerve it's been hiding in, emerging at a dermatome. That's a specific area of skin served by that nerve, usually wrapping around the torso in this band-like shape. And it just erupts, creating localized irritation, extreme sensitivity, and this really painful, ugly, blistery rash.
The stakes in this second phase are entirely different. I mean, chickenpox was mostly just a mild, full-body nuisance for kids, but zoster, because it's traveling directly along pain sensory nerves, shingles can be absolutely devastating. We're talking agonizing pain. If it emerges around the eye, it can literally cause blindness, and some people are left with a permanent, life-altering pain condition called post-herpetic neuralgia, or PHN.
But thankfully, we haven't just accepted this. Phase 4 is our counteroffensive, vaccines.
Modern medicine has mounted this massive decades-long fight back. It actually started in the 1960s when Dr. Takahashi managed to isolate the virus from a young boy. By growing it at suboptimal temperatures, he created the first live attenuated vaccine. As the years went on, doctors realized chickenpox was actually a massive threat to immunocompromised patients, like kids going through chemo. That really pushed development forward, leading to the first adult shingles vaccine in 2006, and then a totally revolutionary update in 2017.
So the magic behind that very first successful live vaccine was actually hiding right there in gene 62. Researchers later figured out that Takahashi's vaccine strain had 11 specific mutations in this gene, which completely broke the viral glycoprotein GE. And without a working GE protein, the virus just couldn't attack properly. It allowed our immune system to safely study the virus's face without actually getting sick.
Eventually, they took that original live vaccine, packed it into super high doses, and gave it to older folks to try and prevent shingles. The goal was to basically wake up their waning immune response against the latent virus. And, it was pretty solid. It stopped shingles outbreaks about 66% of the time.
But then, science did what science does. It leveled up. The technological jump to the Shingrix vaccine was massive. Shingrix completely ditched the whole live virus approach. Instead, using recombinant technology, it just presents the isolated glycoprotein E and pairs it with this incredibly potent immune-boosting adjuvant called AS01B. The result is a massive, hyper-targeted burst of cytokines and CD4 lymphocytes, the exact weapons our body needs to fight this specific virus. And because of that incredibly precise cellular response, Shingrix clocks in at over 90% effective at preventing the agonizing return of shingles. Think about that. We have literally managed to build a highly effective chemical wall against a master infiltrator.
But it really makes you wonder, doesn't it? Since vaccines are never 100% perfect, and this virus is endemic all over the globe, are we just locked into a permanent arms race with this microscopic mastermind? I mean, yes, we've cornered a 100-million-year-old infiltrator with brilliant science today, but given its insane survival skills and deep cover tactics, how exactly will it evolve next?